Let's take a look at the vector or the cross product. And this is a way of multiplying two vectors together. Normally in 3 dimensions, you could do it in 2 dimensions, but we're going to look at it in 3 dimensions. And if you think we already know about one way of multiplying two vectors together, it's called the dot product. But when you multiply two vectors together with the dot product, you just end up with the value like one number. The cross product for multiplying two vectors together is a much more useful technique because it actually gives us a new vector. It doesn't give us a constant. It gives us a new vector, and that the new vector that we do end up when we do the cross product is actually a link between the two original vectors. So if you look at this formula, if we cross product A and B, so if that's my vector A and that's my vector B, if I cross product those, this is what A cross B ends up looking like. Okay, and the good thing about this is that the new vector, the cross product of these two, is perpendicular to the two original vectors. Okay, so it's perpendicular to B and it's perpendicular to A. Alright, now the formula, the first time you see this formula, there's a lot going on with this, and I think the first time I saw it, I got a little bit lost with this formula. But so the best way I can think to try and explain this is that that's just the constants. That's just the constants, like the magnitude of A, the size of A. So obviously this is telling us that the cross product, if I cross product two vectors, it depends on the size of the vector A. So obviously the longer the vector A is, the bigger the cross product would be. The longer the vector B is, the bigger that this cross product will end up being. It also depends on the angle between the two vectors. Okay, so as this theta varies, that's going to affect how long the cross product is. Okay, so smaller angles, sine theta would be smaller, you'd get a smaller cross product. As the angle approaches 90 degrees, that would be 1, so you'd get like a larger cross product. And so these things here are just constants. Okay, so the cross product, when we cross product two vectors, we get a constant, that's just that's going to end up being just a numerical value, and this is the bit that makes it a vector. Okay, so that's a constant. And when we write a vector with a hat on the top, that stands for like a unit vector. Okay, so the cross product of two vectors ends up being a multiple. See this, the unit vector. This unit vector here is the vector that's perpendicular to the two vectors, but we get like a multiple of that unit vector, depending on how big A is, how big B is, and the angle between them. Alright. The vast majority of the exam style questions don't actually rely on us really understanding this formula, to be honest, that much. We will come back to looking at this formula, but for now, the first thing we should probably do is look at like what this cross product tells us about these unit vectors, and these are the orthogonal base unit vectors. Okay, so like if you think about, if we see the vector I is just written as 1, 0, 0. Like that vector I is like the way we describe moving 1 in the x direction. Obviously j would equal 0, 1, 0, because that's moving 1 in the y direction, and k is 0, 0, 1. Okay, so if we actually just start by looking at these vectors and what happens when we cross product those, it's like a simpler version of this formula, because if you think about it, the magnitude of each of these is just 1. Like they're all a unit vector, they're all length 1. And the angle between them all, because these are all perpendicular to each other, right, we can basically ignore all that stuff for now. The magnitude's 1, the angle between them is 90, so this would just be 1. And when we cross product these vectors, we just get another unit vector out, which is perpendicular to both. Okay, so let's see what I mean when we do this. So if I was going to do I cross j, now the orientation of this is quite important. It's called the right hand rule. Like if you do physics, I think you will have heard of the right hand rule in some other applications as well. So if you wanted to do, the way the right hand rule works is if you were doing A, and the order is important, so if I wanted to do A cross B, then your index finger is A, so A cross B. So if I cross product two vectors, the thumb tells me the direction that we end up being, because you see, as in this orientation, my thumb is perpendicular to those two. So if I do A cross B, I would get this. Okay, and that's how it doesn't work with your left hand, it has to be the right hand because the orientation matters. So if I was going to do I cross J, just try and visualise this. I don't know if I can get my hand to go like that, but like if I was going that way and my other finger J was going that way, can you see that K would be my thumb? I'm not sure if the camera can pick that up, it's quite difficult for me to get my hand to do this, but I cross J would equal K. So if we use the right hand rule, we can see that the answer would be K. Okay. What happened if we did the other way around though, if we were going to do J cross I? So now my index finger is J. I really don't think I'm going to be able to do this on the camera, but if your index finger is going in the direction of J, which is that way, and then I is your middle finger, you'll notice that K is actually pointing, not K, sorry, your thumb is pointing in the opposite direction. Like if I was going to do this vector cross product with this vector, the result would be pointing that way. Like it'd still be perpendicular to them both, but the result would be pointing down that way. Like if you move your fingers around, your thumb points down. So in other words, what that tells us about the cross product, the order matters, and if we rearrange the order, we end up with, it's still going to be very closely linked to this answer, but it's pointing in the opposite direction. Like if you've got K and minus K or A and minus A, that just means that the vector's pointing in the opposite direction, isn't it? Okay. Another application for cross products is if we cross product two perpendicular vectors, two parallel vectors, the answer is always 0. So if you not just I cross I, like any vector cross producted with itself, or like if we use a numerical value answer, so if I was going to do 2, 1, 3, if I cross product that with 4, 2, 6, like those two vectors are parallel with each other, aren't they? The answer would be 0. Okay, and when we actually look at the calculation for the cross product, which we'll show you later, we can see why this happened. But for now, I was just going to introduce like the properties with these unit vectors, because that sometimes can be asked in the exam. Like it wants you to know how to actually work out the cross product in a numerical sense, but it also wants you to know the properties of the cross product. Okay, so I cross J would equal K, J cross I would equal minus K, and if we cross product two parallel vectors, the answer would be 0. So what about if we did J cross K? Maybe pause and think about that for a second, like try and apply the right hand rule. So think about J being your index finger. Try and orientate your hand that way. What would the answer be? Again, I'm struggling to do this here, but if we do J cross K, so my finger was pointing that way with Y, K was pointing that way, my thumb would be going in the direction of I, wouldn't it, or the direction of X. In other words, J cross K would equal I. So from that, we would know that K cross J must equal minus I. Okay, and similarly, if we do K cross I, well, actually, I suppose we should do it in, it makes sense if I did I cross K, wouldn't it? I cross K. What would that give us? Okay, so I is my index finger, K is my other finger, J, my thumb would be pointing that way, which is like negative J. Okay, so I cross K would equal negative J, in other words, K cross I would equal positive J. Okay, these are in your notes, so you obviously you want to highlight those properties, but now that we've seen this, let's actually look at like how this applies to sort of an exam style situation. Okay. Okay, so example 1, we've got prove 2a minus b cross a plus 3b is equal to 7a cross b. And obviously if you do get a question like this, you don't want to start like, we could write it out as column vectors and use like loads of different letters to represent a, but you don't want to do that. Like this is just testing our initial understanding of what are the properties of cross product before we go into the formula. Okay. So we can literally use the cross product, we can expand it out, like it works just as you would think it would work, just as we were multiplying two brackets together. So that would be 2a cross a plus 6 A cross B, and then minus B cross A, and then minus 3 B cross B. Okay, so what we can now say, if we cross product two vectors, a vector is clearly parallel with itself, isn't it? So when we cross product parallel vectors, the answer we get is 0. So clearly they're going to cancel. And then let's see what we're left with. So we've got 6A cross B minus B cross A. And we're aiming to end up with 7 lots of A cross B. So minus B cross A would be the same as minus B cross A, we know is minus A cross B. Like, remember what I was saying earlier? If you were going to cross product them in the other way around, you'd end up with a vector pointing in the opposite direction. So B cross A would be minus A cross B. So that gives us seven A cross B as required. Okay, example 2. We're going to simplify 2A minus 3B cross 3A plus 2B. So that would give us 6 A cross A plus 4 A cross B minus 9 B cross A minus 6 B cross B. A cross A is 0, B cross B is 0, so we've got 4 A cross B minus 9 B cross A, which is minus A cross B, which will give us 13 A cross B. Okay.